I receive one call. Next 5 minutes, I receive 5 calls. Next 5 minutes, no call. No call. Now 2 of those intervals have no calls. Like that, 18 of the intervals, I did not get any calls. 28 of the intervals, I received only one call per 5-minute interval. 47 of the intervals, I received 2 calls in those 5-minute intervals. Okay, 2 calls per interval. So data is clear? Everyone is clear with the data? Okay, good. And 6 or more in a 5 minute, if I receive 6 or more calls, something major has already happened somewhere. So I consider all of that as one bucket. 9 of those intervals had 6 or more number of calls. Now, if I have to see if it fits a Poisson distribution, I have to understand what does the Poisson mean. What does the Poisson mean? Lambda. Lambda has not been given to me. I have to calculate that. What is lambda in this problem? Average number of calls per 5-minute interval. If I have average number of calls per 5-minute interval, then I can get the probability of getting 0 calls, 1 call, 2 call, 3 call. Once I get probability, I can get my expected frequency because chi-square needs, these are all observed frequencies. I need my expected frequency. So for that, first of all, I need to know probabilities of all of these things. Before that, I need to know lambda. So lambda, average number of calls per 5-minute interval. How will I get average? So I am going back basically. If it has to be fitting at Poisson needs lambda first of all. Lambda is average number of calls per 5-minute interval. Average number of calls, if I have to calculate, I need to know the total number of calls divided by total number of intervals. Gives me the average number of calls per interval. Total number of intervals was 50, I know. Total number of calls I need to calculate from here. 18 multiplied by 0, 18 calls. Sorry, 0 calls. 28 intervals gave me 1 call each. So 28 such calls. In 47 intervals, I received 2 calls each. That means total of 94 calls. So that way I can calculate that. Okay. But before we get there, my standard question in the hypothesis testing, what is the null hypothesis here? Exactly. I have to understand what am I trying to find out. Null hypothesis is based on what am I trying to find out. I am trying to find out is the data distributed like Poisson. So null hypothesis is data is Poisson. Alternate hypothesis not distributed as Poisson. So that's either 1 take or 2 take. Oh, anyway, this is chi-square. This is chi-square. I am anyway looking at it. So it's all 1 take anyway. Okay. So now comes the expected frequencies and degrees of freedom. Chi-square needs my degrees of freedom and I need my expected frequencies. Observed frequencies are there. Expected frequencies, like we said, first we calculate the total number of calls divided by total number of intervals. The average number of calls I get 2.39 per interval, per 5-minute interval, that is my lambda. Okay? Lambda I have calculated, but calculated from this data I have, from this sample only. Population lambda has not been given to me. So I am losing a degree of freedom right there. But once I get my lambda, I can get my probability of getting 0 calls. What is that? E to the power of minus 2.39. 2.39 to the power of 0 divided by 0 factorial. I get my probability. Once I get my probability of getting 0 calls, I multiply it by the total frequency. I get my expected frequency for 0 calls. Because this 150 has to be fixed. 150 observed frequencies, 150 expected frequencies. They have to add up. So I multiply that and I get. What is the to the power of 3 divided by 3 factorial. That is the probability. Multiply that with 150, I get the expected frequency. So get the idea? Okay. So that's what we have done. Observe in the expected probabilities and expected frequency. The sum should be adding up to 150, not to 149.5. 149.95, maybe this rounding off, maybe it can happen, but rounding off, you cannot come down by that much. Unless you have a lot more data, maybe. But check, sanity check, the total should add up to 150. So this is what it is. So how many frequencies did I calculate? 1, 2, 3, 4, 5, 6, 7. Do I have it calculated also? 150 is there. So, 1 less. I lose 1. I also lost 1 degree of freedom for calculation of the lambda itself. Okay? Lambda is an estimate from my sample. So, 7 minus 2. 5 becomes my degrees of freedom. Okay? And that's it. Okay, how do we find this number? We'll get e to the power of minus 2.39. 2.39 to the power of 3 divided by 3 factorial. How do I get this? So you are still awake. Normally, how do I input 6 or more there? What do I do? Okay, good that you are awake. 1 minus of all that. Total probability should be 1. Okay, good. So you don't calculate it here. And so you get 5 degrees of freedom. You got your expected frequencies, you have your observed frequencies, chi-square, you can calculate x-square values, observed minus expected, square divided by expected. That will give you that. Degrees of freedom, 5 degrees of freedom. And at 1% significance level, 15.086. That is my critical value, 15.086. Now I want to see where my sample is. For that, my sample observed frequency minus expected square divided by expected 10.47. Where is this? This is the critical value. 15.086 is here. 10.47. 10.47 somewhere here. 0, 5, 10, so somewhere here. I can compare my critical x square value with the critical value, and I say no, it is not in the critical region. I cannot reject the null hypothesis. Or if you use the R code, it will also give you a p value. Is the p value be less than 0.01 or more than 0.01? This is 0.01. More. This is here. So no better for that. Okay, I count. The p value is more than 0.01. This is 0.01, so this is to the right of that is more than 0.01. I may need water a little bit. So you can't reject. So you can't reject the null hypothesis. What was the null hypothesis? By this time you would have forgotten what was the null hypothesis. It is Poisson. And I cannot reject it. That means I accept it. Okay, it's done. So it is Poisson. The data is distributed as Poisson. Once that is done, now the business has. What will the business do with that? The business understands, okay, the data is Poisson distributed, the number of calls I am receiving is distributed as Poisson. Now I can calculate probabilities for getting 7 calls, 10 calls, whatever, and I can staff my people so that none of the emergency calls are missed. See, I can take decisions. I have to not do that. I am more confident about how many calls I will receive. 3 calls, what's the probability? 5 calls, what is the probability? Okay. Great. So that is chi-square distribution. Goodness of fit test. We just took a break, but the first break was late. If you So the casino is really happy that using statistics, they have found that their slot machines are rigged. So now they are thinking everything in the casino is rigged. So they want to understand now not about the slot machines. The slot machines have been rigged. They are fixing that. Now they want to understand if the blackjack tables, something fishy is going on with that also. So blackjack tables, those of you who are great gamblers here, please forgive me if I say anything wrong here. But that is a blackjack table. These are the casino employees who manage the show. They are called croupiers, or as some of the people in the past batches educated me on gambling, they are also called dealers. Blackjack dealers. Okay, so there are some experts in every batch. Okay, blackjack dealers. Maybe I should just change the name next time. Okay, so blackjack dealers. So these are the dealers. Casino wants to know if they are dealing only on top of the table or under the table also. So are they helping the customers win and then sharing some of the but even if you share, you cannot not deposit in the bank. How you have to make it something. Great. Okay. So anyway, so what they want to see is the outcome of the game. There are three outcomes in the blackjack game. Win, draw, or lose. Is the outcome dependent on the dealer? If it's random, then nothing should matter. But if there is an unusually high number of wins for the customers when playing against croupier A, then chi-square test will capture that. So, is the outcome of the game independent of the croupier? Is what we need to understand. So, independence of variables, second application of chi-square. These are the observed results. Against croupier A, 43 people won, 8 drew, 47 lost, 49 2 44, 22 5 30. That's what the observed results are. How do I get expected? There is no probability distribution here. This is a different type of problem for chi-square. There is something called a contingency table that we have to identify. The rest of the analysis remains the same. So I have to get my expected frequency anyway. Observed frequency is there. Expected frequency I need to get, but there is nothing called a probability distribution here, unlike the previous one. Null hypothesis, independent. I am trying to understand if the outcome of the game is dependent on the croupier or the dealer. No. The null hypothesis, they are independent. They are all nice people, no cheating going on. Okay? Their outcome is independent of the dealer. But I need to calculate my expected frequency, for which we have to now come back to our probabilities that we learned in the second class. Okay? If they are independent, if the probability, if the outcome is independent of the croupier, then what is the probability, joint probability of winning and playing against croupier A? Winning and A. The dealer A. If they are independent, that would be probability of winning multiplied by probability of playing against croupier A. That's my, and my null hypothesis is they are independent. Okay. So, probability of winning, how do I get that? First of all, in this table, I just add them up, get the totals, both the row and the column totals. So, how many games were won? 43 plus 49 plus 22, 114 games. How many games were drawn? 15 games, 121. Total number of games, 250. That is what this is. How many games did dealer A manage? 98. Dealer B managed 95. Dealer C managed 57. Sum of all these has to add up to 250. Okay. So now I want to get my probabilities of winning. What is the probability of winning? 114 or 250. Marginal probability. Only one variable I am interested in. And you thought, why were we talking about all of those things? So 114 divided by 250. What is the probability of playing against croupier C? 57 divided by 250. C, I asked C. 57 over 250. That's the probability. What type of probability? Marginal. And the calculation is classical or frequentist or subjective? Frequentist. I'm calculating. That's the frequentist approach to calculate probabilities. Okay. Now, if they are independent, probability of joint probability of winning and A is, at this time I don't want to calculate because in the next slide it becomes so easy that you can forget all about probabilities and still be able to calculate. Okay. So, total wins divided by grand total multiplied by total A divided by grand total. Total wins, this divided by this multiplied by this divided by this. That's what this is. This is the probability. So my expected frequency, probability multiplied by total frequency gives me the expected frequency. So expected frequency of this number, this is the observed frequency. Expected frequency, this was the probability of winning and A multiplied by total frequency. So one grand total cancels out here. Total wins multiplied by total A divided by grand total, which means total wins is the row total, total A is the column total, and grand total is the total total. So now the expected frequency of this is 114 multiplied by 98 divided by 250. Easy. Now, without forgetting all our probability, what is the expected frequency here? 15 multiplied by 57 divided by 250. But don't think that they will keep saying wow, so then I will just start giving the chocolates. Really wow. Only when it is wow, say wow. Okay? Yeah. So now that's easy now. So I can get all my expected frequencies. I have observed frequencies. I calculated O minus observed minus expected squared divided by expected. I get my x square value. Compare it with the critical value. How do I get my critical value? I need to know my degrees of freedom. Now that is another thing I will ask you. So this is my expected frequencies. Some people create a new table, some people just put in brackets right next to that. Doesn't really matter. Software will do its job. So I calculated all of that. Observed 43 won against A, 8 drew, 47 lost. Against dealer B, 49 won, 2 drew, 44 lost. These are my expected frequencies. Sum has to add up to 250, 250. Observed minus expected square divided by expected. 5.618 is my x-axis value for my x square statistic. I have to compare it with my critical value. Now degrees of freedom. How many degrees of freedom should I be calculating? 2. If I calculate 2, I will get all the others. 2 minus 2 minus 1 rows and 2 minus 1 columns. So what will the answer be? 1 multiplied by 1? 1? Is 4, yeah, 4. So again, anybody who is not getting it, he is getting too much of chocolate. Ensure that you take it from him. So what Prasun says is, if I know any 4, so if I know this and this, I don't need to know this because row total is known. Number of wins I cannot change. That has to be fixed. If I know this and this, I don't need to know this. So So 4 degrees of freedom at 1% significance level, 13.277. So my critical value is 13.277, corresponding to 1% significance level. It is 13.277. My sample was at 5.67618. What do I do? Fail to reject or accept the null hypothesis. What was the null hypothesis? Not quite wrong. That problem is over. They are independent. That's a good one. Try to throw me off because I said by the time we come to this answer in this question, we have forgotten what we were looking for. Yeah, they are independent. The outcome of the game is independent of the dealer. And I cannot reject that null hypothesis. So I have to accept it as independent, which means those guys are not cheating. Yeah, just because their slot machines were rigged, not everything in your casino is messed up. This thing is going fine. Okay? So that's the decision done. One more example of this same independence test and then we will move on. May 8th, yeah, this year, right? Same. Alert over painkiller epidemic. People just keep taking medicines just like that. Just like that. And that is causing many other problems to come. So there is widespread abuse of prescription drugs for a number of reasons like getting high, reducing appetite, relieving tension, feeding an addiction, etc. etc. People are doing that. Variety of reasons. Prescription drugs being taken unnecessarily. Okay, and so there is a problem there. So National Council on Alcoholism and Drug Dependence wants to understand if there is a dependence of the type of prescription drug abuse on the age of the patient. So the type is either people take pain relievers or some tranquilizers or sedatives or some stimulants. So is pain relievers, maybe older people are using them. Many people do. They are a lot more pain. Tranquilizers or sedatives. Basically too much of tension, just relax. Or stimulants. Some younger generation, high on something. Just chill out, man. So is there age dependence? So more people taking this, more people taking this and more people taking that. Is there some kind of dependence on age with this? We collected some data on who is abusing what. This is 309 total number of people. Number of people, young people 139, younger people 109 and youngest people 69. Okay? And number of people taking pain relievers is much less. So now we know the process. What do? I have the observed frequency. What should be the expected frequency here? 101 multiplied by 148 divided by 309. That's it. Observed frequencies, expected frequencies, known. Null hypothesis before that. What's the null hypothesis? Independent. The type of drug abuse is independent of the age. Anybody takes anything, basically. Okay? And the other one is not independent or dependent on age. So we calculated the expected frequencies from the expected. But same problem as last. Degrees of freedom, same. Any 4 I calculate, the rest are calculated automatically. Same problem, so it's okay. So 4 degrees of freedom, and again I think 1% is what we were looking at, 13.277. 13.277 is this value. Where is my critical value? Critical value 59.41. You fill in these blanks. 59.41. 13.277. 0, 13, 26, 39, 52. Somewhere here. What do we do? Reject the null hypothesis. What was the null hypothesis? Not quite sure. of squares. Sum of squares is nothing but total variation. Squared variation, deviations, I am calling it sum of squares. Average sum of squares gives me the variance. I am averaging them. So, sum of squares. So, this xi minus x bar squared becomes s square times n minus 1 divided by the population variance. I have a sample variance. I am making inferences about a population variance using chi-square. Okay. So, let's just use this problem. There is nothing else to teach here. Yes. This is chi-square actually. Z square. This is the formula. First slide when we looked at chi-square, we also said it was nothing but a z square. Many z squares added together. Z square is, z value is x minus mu divided by sigma. Which one? Yeah, so this and this put together comes to this. So, this is what? Xi minus x bar squared. This is okay? This part is okay? Those were questions? This is what we started off with. Chi-square is z square. Here, xi minus x bar square. If I use this also is no variance. What is xi minus x bar square? S square multiplied by n minus 1. I just replace s square times n minus 1 in this formula. S square times n minus 1 divided by sigma square is chi-square. Sure? Just rearranging this and this. This is common to both. So I'm just replacing them. Okay, so a manufacturing company is producing ball bearings 2.65 centimeters in diameter, and the customer has put a specification that the variance should be less than 0.001 square centimeters. So, obviously quality